What I would like to do now is try to get a score comparison even basis. I'm going to do it actually by using the our original data set, which I'm going to rerun again just because it's up here, and I'm not going to worry about timing right now. So I need to resplit that data because I've redefined df. Okay, so you're running the top cell and then this cell that redefines x and y. Okay, and again, you can leave the time up there. It doesn't really matter. And so what I want to do though is I want to get clarity on the different parameters that are used. This train test split doesn't matter because we're going to use the same. I mean, I don't need, sorry, it matters. I'm thinking ahead, I don't need a random state there. Okay, I want to use a random state. And so like this is okay to keep really, right? But the key is that we want to know like what are the defaults? And so if I put in, okay, the XGB classifier, you can see it's showing me the defaults, right? So I'll put in some of them. Max depth is given as default of 3. I'm just copying out what they're giving me. Learning rate to 0.1. These are all things that we'll adjust in the future. In estimators equals 100. What else do I have here? What we're really looking for are differences between booster GB tree. I'm looking for differences between this and the gradient boosting classifier. Okay, so if the gradient boosting classifier, learning rate is the same, estimators is the same, is the max depth. Max depth is also the same. So what is in fact different? Wow, maybe they do have the same defaults at this point. The criterion freedom equals MSC. I'm not sure about that. So it looks pretty comparable. Again, I can go back up here to check. Yeah, it all looks pretty comparable actually. Okay, so I think what we want to do here, see, like I could tell you some of the XGBoost models, you could say, like outside of sklearn have different max depths. Okay, and so to do a fair basis of comparison, you want the same max depth, for instance, the same learning rate, things like that. Learning rate can also be different in different setups, but they look about the same. So it could be. I would like to think that random state 2 is not the only thing that is actually going to be how do you say it? Different. Meaning that like if we give both of them the same random state, it's a more even basis of comparison. We already defined this model, but I think now the point is I want to do this with a random state of 2. Wait, well, we could do the classifier, but really what we want to do is the gradient boosting classifier. Okay, that's the main one. And just to see them both, we'll put them up here. And it just allows for some of the random elements to be the same. Now, okay, it did score better, though very slightly, right? 87.2 to 87.1. Okay, and you may wonder, well, what if you change the random state? What if, and I think you put in any number. Could it potentially flip? Maybe. You get a different score. Let's find out. Put a random state equals 5, random state equals 5. We've got the same 87.2. Uh-oh, I tried to move this. I think I pressed the wrong thing. 87.1 again. And note that it didn't actually give those scores, initially gave different scores. So it's not like I was going to get those scores. Let's try something different, like 999. But one of the big pieces is on the split. It's actually on how the data is actually split. Right, so maybe we'll keep seeing the same scores here. And you can check like the random forest. We are seeing the same scores. So I think it's more so on the train test split than anything else. Right, so we continue to get this like little 1 point advantage. It's also better than the random forest. Now, is that significant? So in itself, maybe not, but I can tell you from experience of running these that when you have the same setup, okay, the same model with XGBoost and the gradient boosting classifier, XGBoost performs better. And it's designed to do so. And why? Well, it has some built-in. It's a good question. It gets sophisticated, you know. It's got some extra built-in regularization techniques, and they have their own kind of optimizers, okay? And you can see that the differences are slight, but they are consistent, okay? And I'm not saying that based simply on what I'm showing you here. I'm saying it based on my additional experience that I have like running other stuff. I mean, the exoplanet one took a long time to run, so I don't want to run that one again. When you have a different random state, you know, you could end up with different results, right? The one gradient boosting could definitely outperform it. If we check, did it? No, it was 99.0 to 99.2, right? So a slightly bigger edge there, not a lot, but you know, when you're building machine learning models, if you see one model that's consistently outperforming the other, yeah, you want to use that model. And the question that naturally arises for me is, does XGBoost render gradient boosting? I mean, it is a gradient boosting, okay? So does the gradient boosting classifier in sklearn, okay, that one, right? It's right here. Is it rendered obsolete by the XGBoost model, by the XGB classifier? I would say yes. There's simply no advantage to using it. You can see XGBoost when the data gets bigger is much faster, and it consistently performs better, okay? So the other thing is that gradient boosting is arguably the leading model in, you could say, machine learning when it comes to tabular data. Okay, these are not neural networks. Neural networks run the show when it comes to unstructured data like images and text. But when it comes to, and they're also really good at like tabular data. But when you're looking at non-neural networks, okay, XGBoost by default, on average, usually is your best bet as far as a go-to model to get a great machine learning score. Okay? Now, we don't rest on that in this class. We're going to do more. We're going to learn how to make it stronger, okay, and more accurate. But with all other things being equal, again, XGBoost on average will do better. Now, does it render random forest obsolete? Absolutely not. Random forests are a different model, and you can see like they're pretty. Gosh, they look like they got the exact same score here. Actually, it's kind of interesting. And you know, they do outperform XGBoost at times. So you know, you certainly don't want to like let go of random forest. What about the individual models like decision trees themselves? You know, decision trees just aren't going to do better than ensembles. Like they're useful in terms of building the ensembles. So you know, they're far from obsolete. They are the building blocks of random forests and extreme gradient boosting. Okay. What about linear and logistic regression? Different models. They will always be big players in the machine learning world. Linear regression only does so well because model is not typically linear, whereas logistic regression tends to do well. But on average, these models just perform better. And on average, my experience is that XGBoost is basically the best. You know, it's won Kaggle competitions for good reason. Okay. It is a leading player in the field. Okay. And so the build up to this point has been this. It's been to really to try to get you comfortable building machine learning models. Hopefully you see a lot of the commonalities between, you know, building different models in sklearn. Like on one level, it's just you got to know whether it's a regressor or a classifier, and you've got to call it out correctly. And then we've also looked at the appropriate ways to kind of score the models using like cross-validation, train test split. We've looked at how to do hyperparameter fine-tuning, right? How to adjust like in estimators and max depth so that your model performs better. And at this point, we basically arrive at kind of a general conclusion that, okay, so XGBoost seems to have the most going for it going forward. And so what we're going to do in the final few lectures is focus exclusively on XGBoost and see what we can gain from it. Now, while we're doing that process, we will continue to add in new machine learning, like little pieces here and there. Like when we look at the exoplanet data set, which we had here, okay, the data set was imbalanced, right? And I asked you all to think about it, like if you have an imbalanced data set, then let's give her Y value counts. There it is, right? You know, it's easy to build a model that's really accurate because you can just say, hey, predict everything as a 1. And it'll say, oh, wow, you've got 5,050 correct out of 5,087. What's that? Let's find out. So what is 5,050 divided by 5,087? What do you know? It's 99.27%. So there's a great machine learning model, but we've talked about, right, the variance bias trade-off and how that is not going to fit well the new data. You're not going to get any exoplanets. Quite the opposite. So we're going to look at new scoring metrics, you know, and some other techniques along the way. We've looked at graphing, how to graph like in estimators. We've really looked at a lot of content, and I'm excited to kind of go in a little bit of depth with XGBoost and to keep going forward. Thanks.